Here is your test review. All right, so first part where it says for each of the following, write an equivalent expression. All right, so I have two logs with the same base, so I'm going to create that into one log. This is subtraction, so it becomes division. Here I have 3, but before I combine them, I need to make these coefficients into exponents. So we'll get the log of x squared minus the log of 3, nothing happens to that one, minus the log of y to the 5th. Now remember, the easiest way to do this when you have more than 2 is to go ahead and do log of whatever base it is. I'm going to make it into a quotient. Everything that's positive, so this is the only positive one, it goes in the numerator. Everything that's negative goes in the denominator, so this is 3y to the 5th. All right. Which of the following expressions is equivalent? Okay, so remember that the square root of y is really just y to the 1/2 power. So when I'm splitting it apart, so the opposite of what we just did there, I'm going to have the natural log. Everything in the numerator is positive. So I can split that into 2. So that's the natural log of 2 plus the natural log of x cubed. Since this is in the denominator, I'm going to subtract natural log of y to the 1/2 power. I could leave it as the square root of y when I write it like that, but I want it as the exponent so I can bring it out front, because then I'm going to have the natural log of 2 plus 3 times the natural log of x minus 1/2 times the natural log of y. And when I look over here, that would be B. Okie dokie. So same thing here. I'm going to split this apart. So I'm going to have log base 2 of 8 plus log base 2 of x plus log, nope, not plus, sorry about that, minus, because it's in the denominator, minus log base 2 of y cubed. Now, I know most of you aren't going to complete this before you actually look at your answer choices, and when you look over there, this one doesn't even have 3 terms, so it's not D. And then these don't even have a log there. So I'm going to have to take care of that. Now I can eliminate one more because I know that this 3 is going to come out front and it's not 1/3. So now I got a 50-50 shot here. I do not get to just drop the log. So chances are pretty good it's not 8, but I don't want to guess. I can rewrite this as log base 2 of 2 to the 3rd plus log base 2 of x minus 3 times log base 2 of y. All right. Then I can bring this 3 out front, so this becomes 3 times log base 2 of 2 plus log base 2 of x minus 3 times log base 2 of y. All right, so this one has the same thing there. That one's all that's different is this. Well, log base 2 of 2 is just 1, so that's why my answer is B. All right, so when we're putting them together, remember that we first have to make these into exponents. So I'm going to get log of x to the 4th minus log of 4 plus log of y to the 1/3 power. Okay, so then I'm going to make it into 1. Everything that is positive goes in the numerator, so that's x to the 4th. This is negative, so the 4 goes down here. This is positive, so I get y to the 1/3 in the numerator. And y to the 1/3 is the same as the cube root, so my answer is B. All right, so now we are solving. Now I'm going to do this. I'm going to do number 1 2 different ways, because I had told y'all, like I showed you one way when we did this, and then I kind of did it a different way once we got to inequalities, and I wasn't trying to confuse you here. But one way to do this, let me kind of split this here, is I can rewrite it as 10 to the second, I can go around 10 to the second power equals this. So 10 squared equals x minus 1, right? So that gives me 100 equals x minus 1. So 99 equals x. Now, the way that I probably should have done it from the beginning, because again, there's more than one way to do a lot of things, is you get the same answer, and it's the same process, it's the same concept. It just makes the inequalities easier. So since log base 10, I'm going to make both of these the exponents. So basically I'm doing 10 to this power equals 10 to this power. Well, 10 to the log base 10, those cancel out. So I get x minus 1 equals 10 squared. You see I get the same thing, but it's in a different order. When it's equality, it doesn't matter. When it's inequalities, it does. So that's why, x minus 1 equals 100. Oh, I put 99. What a dork. Okay, x equals 101. This, I add 1, not subtract. You get the same answer if you do it correctly. There you go. Alrighty, and then we're supposed to always check, right? If I've got logs, so because it also tells me check for extraneous solutions. I take my 101, I substitute it back in. I'll be taking the log of a positive number. I'm good to go. All right, so here, before I can raise these, I've got to either make that an exponent, or because I just have a single term on both sides, I could divide both sides by 4. I think I would rather divide both sides by 4. So this will give me log base 3 of 2x equals 2. Then I'm going to do my power thing. My base is 3, so base becomes 3. This essentially cancels out, and I get 2x equals 3 squared. So x equals 9 over 2. And just leave it as 9 over 2. And if I substitute that back in, I'd be taking the log of a positive number. So I'm good. All right, so here, before I do anything, I need to move that 4. So I have the natural log of x over 3 equals 3. Now I could split the log on the left, but I really don't want to do that. The base here is e, so I raise both things to, or I make e the base there. So those essentially cancel out, and I get x over 3 equals e cubed, and e cubed is just e cubed. Multiply both sides by 3, and x equals 3e cubed. And when I substitute this in here, 3e cubed divided by 3 is e cubed, which is a positive number. So I'm good, even if you have no idea what the value actually is. Okay, so number 4, I need to combine on the left first. So I'm going to get log base 10 of x over 3, and that's equal to log base 10 of x minus 4. And essentially we get to drop the logs, but the reason that we get to drop the logs is because if I make 10 the base and raise it to those powers, then essentially those cancel out and those cancel out. So I get x over 3 equals x minus 4. Then I would like to get rid of the 3 in the denominator, so I'm going to multiply both sides, which gives me x equals 3x minus 12. So then if I go up here, I'm going to get negative 2x equals negative 12, so x equals 6. I check my solution, put 6 in here, I'm good, put 6 in there, I'm good. All right. On the left, I'm going to combine those. So I'm going to get the natural log of x plus 2 times x minus 1 equals the natural log of 3x plus 13. So remember, now single log on both sides. Essentially, I can drop them, but that's really because the base is e. I'm taking e to those powers. Those cancel out. I'm going to go ahead and multiply that together. So that's going to give me x squared plus x minus 2 equals, those essentially cancel out, 3x plus 13. This is a quadratic. I'm going to set it equal to 0, and I'm not going to make up math. So I'm going to get x squared minus 2x minus 15 equals 0. So when I factor, I'm going to get x minus 5 and x plus 3 equals 0. So x equals -3 and 5. So when I substitute them in here, -3 right here, -3 plus 2 is a -1. So that's a no. 5 plus 2 is good. 5 minus 1 is good. Put 5 in here, I'm good. So my answer is only 5. All right, number 6. I need to combine on the left. So this is going to give me log base 2 of 4x over x minus 2 equals 3. Now, can I cancel the x's out on the left, you think? Absolutely not. I cannot just drop the logs here either. That base is 2. So I'm going to make the base 2, make them into exponents. So those essentially cancel out, and I get 4x over x minus 2 equals 2 to the third power. So 4x over x minus 2 equals 8. I'll go up here. So I'm going to multiply both sides by x minus 2. So I'm going to get 4x equals 8x minus 16. So negative 4x equals negative 16. X equals 4. So then I'm going to substitute this into here. That'll be okay. In here, that'll work. So my answer is 4. All right, so I need to combine the left here, but first I need to make that an exponent. So this is going to give you the natural log of x plus the natural log of 3 squared equals the natural log of 2x plus 13. So on the left then, I'm going to have the natural log of, so 3 squared is 9. This is going to give me 9x equals the natural log of 2x plus 13. Okay, base is e. Make the base of the exponent e. Those essentially cancel each other out. So I get 9x equals 2x plus 13. So 7x equals 13, and x equals 13 over 7. Substitute it in here, I'm good, and here I'm good. That is my answer. All right, number 8. Here are f and g. I'm going to solve f of x equals 1 for all values of x. All right, so I'm going to have 1/2 times log base 10 of x minus 3. That's not a 3. Hello. Minus 3 equals 1. All right, now I could make that 1/2 into an exponent, but I could also multiply both sides by 2. So I'm going to do that. Log base 10 of x minus 3 equals 2. So now I have a log equal to a number. The base of the log is 10, so I can make that the base of my exponent. So those essentially cancel each other out. And I have x minus 3 equals 10 squared. So x minus 3 equals 100. And x equals 103. Check myself. Put 103 in here. I'm good to go. All right, then g of x for 8. So 3 times the natural log of x plus 2 equals 8. All right, so again, I could make 3 an exponent, but instead I want to divide. So I just think that would make easier. So this is going to give me 8 over 3. All right, no biggie. The base of the natural log is e, so I make e the base here. Those essentially cancel each other out. So I'm going to get x plus 2 equals e to the 8/3 power. So x is equal to e to the 8/3 minus 2. And so if I take this and I substitute it in here, like I have no idea what e to the 8/3 is. I guess I could figure it out. But if I put this whole thing in here and then I have minus 2 and then plus 2, it just leaves me with this, which is a positive number, and that's all I really care about. I'm good to go. All right, number 9. We're going to rewrite j of x as a single natural logarithm without negative exponents. In any part of the expression, your result should be in the form natural log of the expression. So it's telling you how much to condense and basically what to do with that. I'm not solving. Notice it says rewrite. It does not say solve. I don't have anything to solve. I'm just rewriting. And so let me just start by rewriting j of x as it is. You wouldn't necessarily have to rewrite it, but I'm going to. All right, so I need to first make these into exponents. Like, because I'm not solving, I don't have the option to divide or multiply, either way, but I'm making them into exponents. So this is equal to, so j of x is equal to the natural log of x to the 1/3 minus the natural log of y to the 4th. And then that means that j of x is equal to the natural log of x to the 1/3 power over y to the 4th. And you could have the x to the 1/3 could be the cube root. But I'm rewriting j of x. My final answer needs to be an equation, which means you have to have the j of x part there. Don't get lazy. All right, so we're going to do the same thing for k of x. So let me rewrite that down here. K of x equals 3 times log base 10 of x plus 2 minus log base 10 of x plus log base 10 of 5. Okay. Don't get lazy. Write stuff out so you don't make ridiculous mistakes. Again, I'm not solving. I'm rewriting. Okay. And it tells me I should have one single log just like that. And I need, I can't divide everything by 3 because I'm not solving anything. It has to become an exponent right here. That's the only one I have to do. So let me just rewrite that. K of x equals log base 10 of x plus 2 cubed minus log base 10 of x plus log base 10 of 5. Okay, so I have more than 2. It's simple. Don't overthink this. We're going to make this, oops. We're going to start by saying k of x equals log base 10. Make my fraction bar. Everything that's positive, so this one's positive, this goes in the numerator, x plus 2 cubed. I don't have to actually cube it. I just write that. This is negative, so the x goes in the denominator. This is positive, so the 5 goes in the numerator. Boom, you're done. Okay, that is it. All right, function k is given by this. We're going to solve k of x for 7e. All right, so I'm going to take 2 times e to the 3x minus e equals 7e. Okay, so I can move that this e over to the right-hand side. So this is going to give me 2e to the 3x power, and I'm going to add that, and that'll give me 8e. Okay. Then I need that 2 right here. This is being multiplied in front of here. I'm trying to get that x by itself. So I can divide both sides by 2. That'll give me e to the 3x equals 4e. All right, so now the way I get the exponents out of, or the variables out of the exponent, is I'm going to take the natural log of both sides. So I'm going to take the natural log of e to the 3x, and that's equal to the natural log of 4e. So on the left, I'm going to bring this out in front and get 3x. Actually, I don't even have to bring it out in front. Well, like basically this cancels itself out, but let me show you why. I bring that out front, and then I have the natural log of e, and that's equal to, here I can split this, the natural log of 4 plus the natural log of e, Now remember, natural log of e is 1, and that is 1. So on this left-hand side here, I have 3x times 1. That's just 3x. That's equal to the natural log of 4. This one, though, is plus, so I do have to put that 1 there. And I'm trying to get x by itself, so now I divide, and I get x equals natural log of 4 plus 1 all over 3. Okay, and it's fine to have like a natural log in your answer like that. Now, I could take the log of both sides on 11 to get the variable out of the exponent. However, that's going to make things a little bit more complicated because I would have to actually get a number in the end. So my other option is this, which is not always an option depending on the values, but it's an option here. I can get common bases on both sides. So of 4 and 8, I think my common base would be 2. So I can make this 2. So 8 is 2 to the third, right? So 2 to the third to the 2x plus 1 power can be equal to 1/4 is the same as 2 to the negative 2 power. So that means this is 2 to the 6x plus 3 power, and that's equal to 2 to the negative 2 power. So now, I mean, again, I have common bases, so I can take the log base 2 of both sides. That's what's, again, officially happening. But if these two are equal, then 6x plus 3 has to equal negative 2. So 6x has to equal negative 5, and x has to equal a negative 5/6. Okay. All right. Calculator required here. All right, here we go. Starting in 2018, a biologist studied a population of largemouth bass in a particular lake over several years. In 2019, t equals 1, there were 430 largemouth bass in the lake. In 2023, t equals 5, there were 715 largemouth bass in the lake. So I have two ordered pairs already. 1, 430, and 5, 715. Okay. The number of largemouth bass in the lake can be modeled by this function right here. Tells me exactly what it's supposed to look like. L of t is the number of largemouth bass, and t is the number of years. We're going to use the given data to write two equations that can be used to find the values for constants a and b. Do not miss this part. It does not get much easier than this. This is t, this is L of t. This is t, this is L of t. Okay? So my first one is going to be 430 is equal to a plus b times the natural log of 1. My second one is going to be 715 equals a plus b times the natural log of 5. I'm taking that from the ordered pairs. I am not solving anything. I am not simplifying anything. I am just writing it down. Now, this is a calculator question. Could I find a and b by hand? Yes, I could. And if you looked at the review I originally posted in the key folder, I told you it was last year's because last year we had to do some stuff by hand. We absolutely do not have to do that here. So we are going to use our calculator, and we are going to add a table. We are going to type in our information. Our x's are 1 and 5. Our y's are 430 and 715. Oops, I don't know what I'm doing there. Okay, back it on up there. All right, I'm going to zoom that in for myself. I'm going to do a regression, logarithmic. Now look what they gave me here. A plus b times the natural log of x. Look at what I want here. A plus b times the natural log of t, which basically is by x there. So this one, I don't have to manipulate in any way. It's not asking me for log base 2. It's not asking me for t plus 1. Like, that is it. But here, it has y and x, right? We're answering this question, so we need to put it in terms of this question and say what this has here. Oh, actually, I'm not writing the equation. What am I saying? This literally says find A and B. Got a little ahead of myself there. A is equal to 430. I'm not writing the equation. And B is equal to 177.08046. Okay. I do not need to write the equation, therefore I am not writing the equation. Because if I was to write it and do something incorrect, I would not get credit for that. Plus, it literally asks me for A and B. Answer the question that's being asked. Now it says to use the given data to find the average rate of change of the number of largemouth bass in the lake from t equals 1 to 5. Express your answer as a decimal approximation. Show the computations. So that means this goes from 1 to 5. So I'm going to do L of 5 minus L of 1 over 5 minus 1. I write that step first. Equals to, and then L of 5 is 715 minus L of 1, which is 430, all over 4. Okay. Now remember, this is the slope, right? So I'm going to show you something. When we come over here to type this in, because we want the decimal, instead of just typing it in, here's one way we can, we're not really storing a number, but we're saying what the number is. So it is the slope. Let's use M. I mean, you could use anything, but I feel like using X or something would just be confusing. So M equals, and then we're going to do our little fraction here, and that is 715 minus 430. And I could put it over 5 minus 1, that's fine, but that's also just over 4. Okay, so I get 71.25, which is not an ugly decimal, and it really is just the 2 decimal places, but we're going to pretend like, I mean, we don't want to type it back in anyway. But that is, they're not always going to come out that pretty. 71.25. And then we really should put units on it. So the numerator, that's the number of largemouth bass, but we can just, fish is fine. Fish per year. All right, so then it says, interpret the meaning of your answer from I in the context of the problem. All right. So this is my slope, and my slope is positive. If my slope is positive, I mean, hopefully we could reason through this, but even if you're not sure if you could reason through it, if you think about your fun chart, here's my rate, right? Okay, so my slope is positive, my rate of change is positive, which means the function is increasing. That's the number of fish, right? Or the population of largemouth bass. So we're going to say the population of largemouth bass, can't just say fish here, is increasing. Now I can't say increasing at a rate because we didn't find the rate. We found the average rate. So increasing at an average rate of 71.25 fish per year. Now, is it always changing at that rate? No, it is not. So I need to say from t equals 1 to t equals 5 years. Okay? Who, what, when? Who? The population. What? Increasing. When? 1 to 5 years. Okay? And how? I guess there's a how in this one too. Alrighty, so it says consider the average rates of change from t equals 5 to t equals p years, where p is greater than 5. Okay, so we're getting bigger. Are these average rates of change less than or greater than the average rate of change? Now, we have the luxury of being able to see the graph, right? We can see what the graph looks like. We can even, zoom out a little bit if we need to. We can see what's happening here. But I can't go by the way it looks. So I'm not sure if it states it here, but I know. So it just says explain your reasoning, but it will say something more like explain your reasoning based on characteristics of the function or something like that. We can't just say because it looks like it on the graph, that sort of thing. Okay, so let's think about what's happening. I'm going to draw myself a little picture here, okay? So here's what's happening. It kind of looks like that, right? And so we're going from 1 to 5, all right? So I'm like 1 to 5, wherever it is, like from here to here, right? And that's what we have found. Now, we found this average rate of change. Well, I can't even get through those 2 little points there. We found this average rate of change. Sorry, it's so hard to aim on this stupid board. Okay, we found that average rate of change. It's asking about the average rates of change later on, right? These rates, if we found more as we went, would they be greater than or would they be less than? Okay, well, as P gets bigger, this graph is still increasing. However, it is concave down. So if we think about our fun chart, okay, since the function is concave down, the rates of change are decreasing. Therefore, they should be less, okay, because they are decreasing. So we need to say all of that. There's going to be a lot of words. We are going to start by restating a lot of stuff from the question. Okay, so I'm going to say average rates of change from t equals 5 to t equals p years. Okay, so I just restated that. And then it's are they less than or greater than? I would say so. Average rates of change from t equals 5 to t equal p years are less than average rates of change from t equals 1 to t equals 5 years. Okay, so less than, and then I just restated that right there. Okay, so I basically restated the question with putting less than instead of, it says greater than or less than. And then I'm going to say because I should say average rates of change of L. Because L is concave down. Now, is L always concave down? The answer is yes. So I don't have to say from T1 to T5. It's always concave down, so that's fine to say that. L is concave down, therefore, rates of change are decreasing. And are the rates of change always decreasing? Yes, because it's always concave down. So on the because part, I don't have to put the like from 1 to 5 or from 5 to P, that sort of thing, because it's always happening. If it was a graph, like this, where it's not always concave down or not always concave up, then I have to state my intervals again. Okay. All right. Here we go. The table above gives selective values of life expectancy in years and income in thousands per year for individuals around the world. The data in the table can be modeled by this function. So we have another L of X situation here. Blah, blah, blah. So this one just says straight up find the equation because, I mean, that makes you do all the other stuff, but so we don't have to write this stuff. And I'm telling you, on the FRQ, you're going to have to write those separate equations and then find A and B like we did on the other one. But that's okay. We need to be able to do this also. So we're going to go to our calculator. We're going to clear this out. We're going to put our data in. I'm actually going to pause and put my data in because it takes me forever. Okay, when you have that much data and you have that many decimals and stuff, make sure you double check what you type in before you move forward, so that you can make sure that you have it typed in correctly, because, you know, lots of places to make a mistake. So I'm going to double check mine because I know what the answer is supposed to be once we get there. So I'm going to hit my little plus sign, let it zoom in. I can already pretty much see my graph because I have so much data. I'm going to do the regression. Linear regression is my default, but I want logarithmic. And this wasn't a thing on the other one, but look at the button I have, log mode. And this is another one where when we click it, nothing changes, but we don't know that that's going to happen. So we need to actually click that button. And remember, the default of what it's going to give you is well, dang it, I don't know that you can see where I can point if I touch it. So A plus B times the natural log of X. So when I come back over here, I wanted A plus B times the natural log of X. So I don't need to adjust anything. I don't have to change my log. I don't have to worry about a +1 because sometimes that happens. So then I can take this and I'm going to write this down. Remember, we're going to write down 5 decimal places just to be safe. And I'm going to make sure I use the correct values here. So on the other one, it was L of T and T. This is L of X and X. So L of X equals A, which is 56.81352 plus B, which is 6.53386 times the natural log of X. Okay. Now we're writing down 5. Last resort, we type those numbers back in, really hoping we won't need to. We would never do that on a calculator. There's times maybe that would happen in Desmos. And what I was going to show you, now that I think about it, on the other one, was the whole point of me showing you on this one. It just occurred to me I didn't need to use it like I was thinking I would. When we typed this in, we had M equals because we defined the variable. We could have used M. I think I'm going to need to do another question with that. There was a reason I put the M in there, and then we didn't talk about it because it didn't come up. All right, back over here. Sorry. All right, so then it says, in 2009, the United States had a per person income of $41,000 and a life expectancy of 79.43 years. What is the residual of this data using the model found in Part A? Okay, so remember residuals. Residual is equal to actual minus predicted. Okay, so the actual value is this 79.43 years, okay, because what we are looking at, L is the, here we go, L is the predicted life expectancy and X is the individual income. So this is my output, This is always for outputs. Okay, that's your residuals for your output. So the life expectancy, that's how I know to use this and not the monies, okay? So I'm going to take my actual, which is 79.43, and I'm going to subtract L of this 41,000, okay? $41,256.10. Right, so when I come over here, my input is the 41,000. So that means when I come back to my graph, add these, my input is X. So I'm going to put here that X is equal to 41,256.10. Okay. And I'm going to hit enter.
Now I could zoom in and out, right? So my input was 41,000. Now, when I look at my graph, my X values that I can see down here only go to 60. Like, why would only be going to $60, right? When this is 41,000. I mean, maybe I need to zoom out to 41,000, or maybe I need to go back and read this and see this is income in thousands of dollars. So $41,000, that decimal shouldn't be here, it should be here. Okay, so it's moving because I'm moving that thousands of dollars there. So I did that. Now, I mean, sometimes y'all I mess up because I mess up, but I did that because that's what some of y'all would do. What's what I might do at some point. I'm not going to say that I wouldn't, as put in the 41,000 because that's what it said. We weren't paying attention, but really, well, if it'll let me, trying to, there we go. And I'm going to move my decimal place to right here. Now that makes a little bit more sense on my graph, right? And then I might just personally want to just, well, if it'll let this, my board. Oh my goodness gracious. I was going to say zoom in a little bit but I'm going to do that just so it's not as close to that blue one. I'm looking for that number right there. Okay. And remember, I wanted my actual minus my predicted. The actual was 79.43 minus, lost my point again. And then I need that 81 number, but I'm going to type in the whole thing, 81.11, 81.11, keep losing it, 815, 815. Oh my goodness. 815. Okay, let me double check since it's much easier if you're actually on the computer. I'm gonna double check that I did that right. Here is my answer right there. Now that 81 number that I used in my calculator, again, we typed in a decimal, not best practice, but what we had to do here. And this is, I don't have to write the 81 number. Like L of this is a perfectly fine way to show that. Then my answer is negative 1.68815. That is my residual. Okay. So let's talk about what that residual means. Okay. So I want you to remember, get in the Wayback Machine in your brain. We had our residuals, even though our graph looks like this, you know, we kind of line it out like that, right? And so this is my x-axis, or my graph. I'm sorry, that is my graph, which is basically like the x-axis. So on the graph is this number right here. And then my residual is negative. That means that this is an underestimate. Okay, so just keep that in mind there. All right. Now, a given country has an average income of 43,500 according to the model found in Part A. What is the average life expectancy of an individual from this country? Okay, so if this is my income, is income input or output? You need to ask yourself that. Income is the input, right? It's what we just did here. So this is $43,000. That means I am looking for L of 43.500 because it is in thousands of dollars. Don't forget that. So then I'm going to come back over here and I'm just going to say X equals, and that was 43.500, which is really just 0.5. And if you get too many lines on here, like I already had this one, but I can turn that guy off. So I'm only looking at this one that I just did, you know, do what you need to do here. And we get 81.464 So over here, this is 81.46419, and those are years. We need our units on there. Now, I'm going to say, what would I'm going to just give you a what if. This is kind of a separate question. What if I asked you, what is the income if we have a life expectancy of 75 years? Okay, so life expectancy is 75 years, and I want to know what is the income. Okay, that means that L of X equals 75, and I want to know what X equals, right? This essentially is Y. So if I come over here and say then that Y equals 75, that's this right here. So if I have a life expectancy of 75 years, looks like my income would be $16,174.29, right? I could do that two different ways. I could put the 16 number and say thousands of dollars, or because it's talking about it like it is, I could say X equals $16,174.29. Okay, so just make sure you're looking, is it the input? Is it the output? So it's either an X equals or a Y equals when you go back over to Desmos. All right, one more, and we're just doing the writing in the A and B here. And notice before we even start reading the question, why we're doing another one of these, because this one looks a little different. So it says, as part of a training program, Stacy began working out in an attempt to lower the amount of time it took her to run 1 mile. Initially, T equals 0, and it took Stacy 570 seconds to run 1 mile. At the end of each week during the training program, Stacy would run 1 mile and record her time. After 4 weeks, T equals 4, Stacy's time to run 1 mile was 465 seconds. I cannot even imagine doing my time to run a mile in seconds. That would be quite comical. So I have two ordered pairs here, 0, 570, and 4, 465, right? And this is M of T and T, so my ordered pairs are T, M of T, right? That's the way they work. So it gives us that equation. M of T is the time in seconds. Now, just because they gave me the time in seconds doesn't mean the function represents seconds, but it does. So those are things we kind of want to pay attention to. And time is in weeks, and that's giving it to me in weeks. So always pay attention to your units there. So we're going to use the given data to write two equations. We're not solving anything, we're writing them that we could use to find A and B, but we don't necessarily have to, but we could. So using this first order pair, M of T is 570. That is equal to A plus B, which I don't know, times the natural log of T, which is 0, plus 1. I leave it. Move on to the next one. 465 equals A plus B, which I don't know, times the natural log of 4 plus 1. And that plus 1 is coming from right here. I'm using the equation that they gave me. That is one of your 6 points on an FRQ. Do not miss that point. Okay? It really doesn't get that much easier. Then we don't have to do anything by hand. We can do this all with the calculator, with Desmos. So I'm going to come in here. I'm going to clear out all this mess. Always start from scratch. All right, I'm going to put in my two ordered pairs into my little table here. So I have 0 and 4, and I have 570 and 465. I'm going to zoom. I'm going to regress. I want logarithmic regression. So I was going to say we got to make sure that we pay attention to log mode, but I didn't even get that far because I got this. Now remember, that happens. And the reason it's happening, if you need to click on this to tell you, logarithmic regressions only work if the first column is all positive numbers. And 0 is not a positive number because it's 0. So that is where my problem is. It's not a problem in the actual function because it's actually t plus 1. And remember that what Desmos is going to give you is a plus b times the natural log of t. Now, we did two things to manipulate the logs in Desmos. One of the things we did was to export, I can't even export it, but we exported it and we manipulated what the log was, right? And if I was able to export the regression, then I could change natural log to like log base 2 or whatever, and a and b would change accordingly. But I can't change that, right? And I don't want to change it from natural log anyway, and it wouldn't let me change it to the plus 1. So instead, I'm actually going to add 1 to my x values. So we either manipulate the regression, which we can't, or we manipulate the x values, which we can. Okay, so I'm going to back that out, and I'm going to add 1 because that is what my equation said. So that is 1. That makes this one 5. Okay, so now I have this. So now I could export the regression, but I'm not going to. Like, I could do this, I could export it, but I'm going to do it, but then I'm going to exit out because I want to show you the difference and remind you. If I export it as a custom regression, if I change anything right here, because it's exporting the whole process, then that's going to change A and B. I don't want A and B to change. These are the correct A and B, so I am not exporting that. What I need is for my function to actually look different. And actually, to be honest with you, I wouldn't have to do it on this one because I don't have to do any more besides find A and B. But on the other questions, you'll have to. So we want to make sure we know how to do that. If I export the regression, I don't want these two numbers to change. So instead, I'm going to export the equation. Now, nothing's going to adjust unless I literally change it, numbers and all. So I'm going to come over here because remember, these are not my x values. Those are my x plus 1 values. So this actually represents x plus 1. And then this is my function because at 0, I should be at 570, which is not what the chart said, but that's what I had to do to be able to get my answer. Now, again, I wouldn't necessarily have to get this blue graph to go farther because this is just telling me to find A and B. But on, if this is on your test, then you're going to have to do more with that actual function. And then at that point, that black one that's up there, I don't want that. Like, that's the wrong one. It's just how I had to get there, so I can turn that guy off. And even those green points aren't even correct. That's really what I have. And that's really what using the actual numbers would give me. I don't even have to write the whole equation. It's just asking me for A and B. So here I get that A is 570 and B is negative 65.24017. And there you go. All right. Now we're graphing. And it says calculators allowed. So here's the thing about the calculator section. Not all of them require the use of the calculator, and not all the questions, even having the calculator wouldn't even help you on some of them. It's just the way it's organized. I don't really have an answer to that. But this is a logarithmically scaled y-axis. So this is my semi-log plot. Remember, your x-axis is spaced out just like a normal x-axis would be, but the y-axis is not. We start at 1, so it's 1, 2, 3, all the way to 10, and this is 10, 20, 30, and so forth. So we are going to plot these points. I have 0, 30. So my x value is 0. Remember, this is 10, 20, that is 30. That right there is A. B is at 1, 2. So my x value is 1. My y value start at 1. This is 2. Pretend like I'm actually on there. Much easier on a piece of paper. C, 2, 400. So I'm here at 2. I'm going to go up to, so I'm here at 2. I'm going to go up to 100. This would be 200, 300. That would be 400 right there. So that is C. 3, 1.5. So here I am at 3. This is 1. This is 2. Now remember, 1.5 is not halfway, okay, because it's logarithmically scaled. So 1.5 is actually closer to 2 on this kind of graph, so it would be somewhere right about there. Remember, you're going to have, this is going to be more of a multiple choice where you would have to make sense of it. So if it is, let's say that I had, pretend like that's right in the middle. If that was right in the middle, that's not going to be 1.5. That's going to be something less than 1.5 because it's halfway, just because of the way that works. So this really should be like there. Again, pretend like it's to the left. Get frustrated. This is D. All right, then 4/11. So here is 4. This is 10. This is not 11. That's 20. So 11 is just going to be a little past that, kind of like there. And that's E. All right. I think we're doing the same thing again here, just more of the, oh, here we go. So this is also logarithmically scaled, but it's not by tens because they're not necessarily always by tens. And it doesn't show you all of the little, stupid thing, I'm sorry. All right. So this is, if I was to write this out, this is by 3. So this is 3 to the 0, 3 to the first, 3 to the second, 3 to the third, 3 to the fourth. Okay. So the reason you don't see as many lines is this is 1, 2, 3, 3, 6, 9, 9, 18, 27. So I'm counting by ones, then I'm counting by threes, then I'm counting by nines, then I'm going to count by 27s, 27, 54, 81. That's what's happening there. Okay. So let's look at what this will look like. My first one is 0, 2. So 0, remember this is 1, 2. So I am right here. That is A. B is at 10, 18. So this is, I'm at 10, I go to 9. I'm going to count by nines. 9, 18, that would be 27. So 18 is right there. And that's B. 26. So here's 20. This would be 1, 2, 3, and then 3, 6, 9. So 6 is right here. So that was what, C? Right, D is 30, 12. So here's 30. This is 3, 6, 9. Then 9, 18. So 9 and 18 right there, right? So let's think about where 12 would fit in there. Halfway between 9 and 18. So let's think about that. This is 9, 18, 27. So it's between 9 and 18 somewhere, right? Well, 9 plus 18 is 27. If I go halfway, that's going to basically give me 13.5. So 13.5, but again, halfway is not halfway. 13.5 would be up here somewhere. 12 is a little less than that, so I would say 12 is also probably a little less than halfway. That looks pretty good there. Let me see. E is 40 and 1.5. So 40, and this is 1, 2, 3. 1.5 is halfway between 1 and 2, which means it would not be halfway on this graph. It would be more than halfway, something like that. Okay, because the way it's stretched up there. All right, last page here. Oops. So this says the function is graphed on a semi-log plot. So it's telling me it's semi-log. So you know the last one was like 3 to the first, 3 to the 0. So this is E. So this is E to the 0, E to the first, E to the second, third, fourth. Okay. Blah, blah, blah. Where the vertical axis has been logarithmically scaled. And remember, this is the only one that will be logarithmically scaled. Which of the functions could be a model for F? Here's what you need to connect here, because this is a very easy question. Is that if this looks linear, I would totally say that this looks linear, right? Since it looks linear on a logarithmically scaled graph, that means your data is exponential. And your data will be in the form of A times B to the X. Okay? If you are not sure, then we can pick points, right? I don't know that I would actually pick the 0, because 0 does weird things. But we could, but let's try it. I'm going to show you mathematically how to actually get this, but if you understand certain things, you don't necessarily have to do that. one of the things that you would have to kind of understand, and I'm just going to erase this because there's a lot going on here, is the estimation for E. You know, having the estimation for pi can be helpful sometimes. So E, which that is right here, it's about, oh goodness, that's too big. E is about 2.7 something. Okay, so this line right here is 2.718, whatever. You don't have to know all that. It's about 2.7-ish. Okay, so let's just substitute. Let's go ahead and substitute in 0. Let's see what happens. F of 0 here, if I substitute 0 in for x, that zeroes out, I get 2. Okay, well, you know, 2 looks like maybe it could work there. F of 0 here, e to the 0 power is 1, so this would give me 3. This is definitely not at 3 if this is at 2.7. This would give me, so f of 0 here, this would give me 2 times e to the 0, so that's really just 2 again, which is what I got here. That looks like maybe it could be 2-ish, right? And then f of 0 here, e to the 0, I would also get 2. So see how that doesn't necessarily help me? I feel like it does eliminate this one. And if you know it's supposed to be exponential, this is clearly not. So now you got a 50-50 shot. But we'd probably rather not have a 50-50 shot. We would rather actually try to figure this out. So let's take the 2 equations that we have it narrowed down to, and let's linearize this. So I'm going to start with C. C is, I'm going to write it down as a y. So y is equal to 2 times e to the x. So to linearize that, I'm going to take the natural log of both sides. So the natural log of y equals the natural log of 2 times e to the x. Okay? So natural log of y is going to stay natural log of y. That's equal to the natural log of 2 plus the natural log of e to the x. Well, remember that we can bring this x out in front, so that's the natural log of y equals the natural log of 2 plus x times the natural log of e. Now this becomes 1. You can also kind of do that here and just have the x. That's fine. You can skip this step. I just want to make sure I'm not losing anybody. And I've lost the natural log part of that, right? Which is fine. So what I have is the natural log of y equals the natural log of 2 plus x. Okay, so let's just pause on that. Let's go over here and let's do d. All right. So for d, I have y equals 2e to the negative x. And I'm going to take the natural log of both sides. Natural log of y equals natural log of 2 times e to the negative x. Okay? So the left just stays natural log of y. Then that's going to equal natural log of 2 plus natural log of e to the negative x. And then remember this kind of, I don't have to go through the other steps, so I can just bring it out front. So now I have the natural log of y equals the natural log of 2, and then that's a negative x. So what we have done when we have linearized that data is we wrote the equation for this line right here. This is my y value, right? This is my y-intercept. And this right here, that 1, is my slope. So this is my y, this is my y-intercept, and this is what's in front of x, and that is my slope. This is a negative slope, this is a positive slope, that is a positive slope. My answer is C. So there you go. All right. Let's look at this last one. A set of data is shown in a semi-log plot above. If an exponential regression is used to model the data, which of the following claim and explanation statements best fit the data? Remember, your ID makes a great straight edge, which I cannot do up here. But this does say, so let's read through part of this again, blah, 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 if the exponential regression is used to model this data. So remember, if the exponential data, if this is good for exponential data, this will appear linear. And when I say appear, I mean, yeah, your eyes can play tricks on you, especially with these weird graphs. So you could lay your ID up there. I'm going to use this little line tool. If I put 2 points through that line, do you see how that data does not appear to be linear at all? Instead, that data appears to actually have a curve to it. All right, so it does not appear to be linear. If it does not appear to be linear, then this is not good. Exponential would be bad. So just knowing that much, let's see what we say. The residual plot will show, so it talks about residual plots. We'll get there in just a second. But then it says exponential model was appropriate. We just said no, so I don't like A. Exponential model was appropriate. No. Exponential was not. Okay, so now I've narrowed it down. I got a 50-50 shot. Then we got to remember what's happening with residuals. Remember, if the residual plot, if it's random and I have no clear pattern, that means life is great. If I have a residual plot and I see some sort of pattern, which we don't see the residual plot, it's asking what would it look like. If it's bad, then we see some kind of pattern. So it says residual plot will show a clear pattern because it is not appropriate. That's how they work. The answer is C.